We now simulate with6LIProxy the generation of lining emission and detection driven by ATDNet locations. This is the global lining network managed by the UK Met Office. We will also add some particle noise just to show which is the type of noise that the matrix will suffer at level 1, that anyway will be removed in level 1B first before going to the L2 to the level 2 products elaboration. So we first have to mark the starting time and the ending time. We have to touch all the fields of data and time. We cannot leave the default one. They are not read at the beginning, the default value, so we have to insert, for example, 12 UTC exactly noon, and we perform a run of 1 second. That is enough to show the phenomenon. We load ATDNet locations and we add particle noise. We make it active, but without switching on the extreme event that simulates the extreme event recorded by geostationary satellites from NOAA. This is useful only to test the removal algorithm, the noise removal algorithm that will be developed by humans. So we make the particle noise active, the process button activates, and we push the process button. So the process starts, so the particle noise is generated, and the run ended. So 6 pulses are read from ATDNet locations generated, with a total of more than 13,000 events detected. We now plot all the events and pulses position, pushing the plot button. We have to wait a few seconds for the plotting, and we will see as red dots or red strikes the particle position and tracks. We have to imagine that is 1 second of detection, so meaning with the frame width we have inserted 1 millisecond. This means 1000 picture, 1000 acquisition of the scene. Particularly if we zoom towards one of the real pulses, you may see that the pulse trigger few pixels on the matrix. So the real goal of the noise removal algorithm is just to clean up all the tracks, the artificial tracks, due to the particle presence, leaving only that natural induced lining events on the matrix. We could shrink the plotting just to enhance few frames. For example, if we put 1/10 of seconds as delta t, we could turn back with the ending time and within the plotting only of 1/10 of a second. For sure the phenomena will be reduced. This now represents 100 frames acquired by lining imager. You may appreciate that in this 100 frame there is no optical pulses. We could go beyond just to catch where are the pulses. Here we have a couple. By pushing the sync button when we switch on and off the starting and ending time, all the plotting is updated accordingly. We could also reduce delta T and shrinking again the time interval that is considered, and this now represents 10 frames. You may understand that in 10 frames only these 2 points are affected by particles noise. So in principle it seems really a huge phenomenon impacting on the systems, but if we consider 10 frames, there are only 2 particles in a usual environment, in a mild environment, at geostationary level, that will be afflicted the instrument. We also have to consider that particle track is normally within a unique frame or as a maximum split in 2 frames. So due to the unusual and unnatural shape of the track, we think that a good particle track removal would be applied to the data and to clean on the data. We push again full time, we return to the starting time and the ending time. We first input on the table above, and again with the plot button we replot all our pulses and events.